All right, everyone, let's get into it. You're here because the EMT2 second midterm is coming up, and you're not just looking to pass, you want to nail it. So we're not going to just skim the surface. We are going to build a full-on strategy for this exact exam based on what Professor Albayrak has made very clear he's looking for. Okay, let's start with maybe the single most important sentence from any of the exam documents. This one rule. It changes everything. It tells you right away that this exam isn't just about getting the right answer. It's a test of how well you can explain how you got there. The correct number is only half the battle. The explanation? That's the whole game. And today, we're going to make sure you know exactly how to play it.
So here's our game plan. First, we'll decode the rules of the exam itself. Then we'll get into the physics, starting with a key strategy for those midterm 1 questions, before we tackle the heart of Chapter 9, that's waves in a vacuum, and different materials, and what happens at boundaries. And we'll wrap it all up with a concrete template for writing that perfect answer that's going to lock in every last point.
First up, let's decode this exam. Before we even write down a single one of Maxwell's equations, we have to understand the rules of the game. Because trust me, on this test, knowing what the professor is looking for is absolutely crucial.
Okay, let's break these rules down. When he says succinct, well-articulated, and correct, he does not want an essay. He wants a clean, logical path from the principle to the answer. The no partial credit part is tough, yeah, but it just means our process has to be perfect. And the negative points, that's the real danger. It is literally better to leave a question blank than to guess the multiple choice and then just throw a bad explanation at it. And of course, if it's not in the box, it doesn't count.
Now, the professor has basically given us a huge gift in the exam info sheet. He's told us exactly what the first 2 questions are going to be. Question 1 is a reloaded midterm 1 problem. Same idea, different numbers. Question 2 is an expanded version. You take a concept from the first midterm and you add a new twist, which is probably going to be time variance or something with waves. This tells us precisely where to start studying.
And that leads us right into Section 2, Midterm 1 Reloaded. Seriously, we are going to use our old work to lock down a big chunk of this exam before we even touch the new chapters. This isn't just reviewing, it's being strategic.
So how you review Midterm 1 is so important. First, do not just read your old solutions. That does nothing. Take a blank piece of paper and resolve every single problem. Second, for each problem, ask yourself, what was the core physics principle here? Was it Faraday's law, Ampere's law? Name it. And third, this is the most important part. You have to think like the professor. How could you expand this problem? What if that magnetic field suddenly starts oscillating? What if those charges start creating a wave? That's probably your question too, right there.
All right, we've got our strategy for the old stuff. Now let's jump into the new material. Section 3, Electromagnetic Waves in a Vacuum. This is the absolute foundation from Griffith's 9.2. Everything else we're going to talk about builds on this. We have to have this down cold.
So where do electromagnetic waves even come from? Well, they're not just some random idea, they pop right out of Maxwell's equations. Think about it. In a vacuum, no charges, no currents. You can take the curl of Faraday's law, and then you can plug Ampere's law into that. You do a little vector identity magic, and boom, out comes the classic wave equation for E. You can do the exact same thing for B. And the speed that just falls out of the math? It's C, the speed of light. It's beautiful.
Now, for the plane waves we always see in this course, there are 4 rules you absolutely have to know. 1, they are transverse. This means the E and B fields wiggle perpendicular to the direction the wave is actually moving. 2, E and B are also perpendicular to each other. E, B, and the direction of propagation, K, they all form a right-handed system. E cross B points in the direction of K, always. 3, in a vacuum, they are perfectly in phase. They peak together, they hit 0 together. And 4, their strengths are tied together by the speed of light. E equals C times B.
Okay, let's talk about the things you'll actually have to calculate. The pointing vector, S, is huge. Anytime a question asks about energy flow, the direction or the power per area, this is your go-to. The intensity is just the time average of the pointing vector. It's what a detector would actually see over time. And don't forget, these waves also carry momentum. The momentum density is just the pointing vector divided by c squared.
Okay, so we've got the vacuum case down. Now it's time to make things a little more complicated, and honestly, a little more interesting. We're going to see what happens when these waves travel through actual stuff, like dielectrics and conductors.
So here are the 2 big scenarios. In a simple dielectric, the wave acts a lot like it does in a vacuum. The main difference? It just slows down to a new speed, v. But in a conductor, everything changes. The free electrons start moving around, creating currents that fight the wave. This makes the wave get damped out, or attenuated, really fast. It loses energy as it goes. And here's a huge difference. The magnetic field now lags behind the electric field. They are no longer in phase.
So, this damping in a conductor gives us a really important idea, the skin depth. You see, since the wave's amplitude is dying off exponentially, we need a way to talk about how far it gets. We define the skin depth, d, as the distance it takes for the wave's amplitude to drop to about 37% of what it started with. For a good conductor, this distance is tiny, which is exactly why metals are shiny and you can't see through them. This is a super common calculation question, so know that formula and what it means.
Okay, this leads us to what is probably the most math-heavy part of this whole chapter. What happens when a wave smacks into a boundary between two different materials? This is section 5, reflection and transmission. Now, these problems can look pretty scary, but I promise you, they follow the same logical steps every single time.
So here's the picture. You've got your incident wave coming in. It hits the boundary. Some of it bounces back. That's your reflected wave. The rest of it punches through into the second material. That's your transmitted wave. The entire goal of these problems is to figure out the amplitudes of the reflected and transmitted waves. We want to know how much bounced off and how much got through.
So how do we actually solve this? We use the same 4 boundary conditions that we learned way back in statics. Nothing new here. The parallel component of E has to be continuous across the boundary. The perpendicular component of B has to be continuous. And if there's no free charge or current sitting on the surface, then the perpendicular component of D and the parallel component of H are also continuous. These 4 equations are the keys. They unlock every single one of these problems.
So here is your 4-step recipe. It works every time. 1. Write out the full equations for all 3 waves, incident, reflected, and transmitted. Be super careful with the plus and minus signs in the exponents. 2. Apply your boundary conditions right at the interface, usually z equals 0. This will give you a system of equations. 3. Solve that system for the 2 things you don't know, the reflected and transmitted amplitudes. And 4. Use those amplitudes to calculate R and T, the reflection and transmission coefficients. And for a quick sanity check, they should always add up to 1. Energy has to be conserved.
Okay, we've gone through all the physics. Now let's talk about the final and maybe the most crucial part, execution. How do you actually write down your answer on the page in a way that's going to satisfy Professor Albrecht's really specific requirements for the explanation?
We're coming right back to this quote because, honestly, this is the whole game. Succinct means don't ramble. Well-articulated means your steps have to make sense, they have to flow logically. And correct means your physics has to be right and your math has to be right. So let's make a template for that.
Here you go, the 4-step perfect answer. Step 1, start by naming the physical law you're about to use. Step 2, write down the general equation for that law. This shows you know which tool to grab. Step 3, show your work. Plug in the numbers and show the algebra. Do not skip steps. This is the explanation he's looking for. And finally, step 4, put a nice clean box around your final answer with the correct units. This structure is exactly what he wants. It's succinct, it's articulated, and it's easy to grade.
And just before we finish, let's quickly go over the common traps where students lose points. First, vector directions. Don't forget the right-hand rule. E cross B has to point along K. Second, boundary conditions. People always mix up which components are parallel and which are perpendicular. Be careful. When you get to conductors, you're going to have complex numbers everywhere. Go slow with your algebra. And please, please, please always check your units. And finally, remember, the explanation is the calculation. Don't write a separate paragraph at the end.
So let's just do a quick final recap. You know the rules of the exam and why explanations are so important. You have a plan for those reloaded and expanded questions. You understand how waves behave in a vacuum, how that changes in materials, and you have a step-by-step method for boundary problems. And most importantly, you know exactly how to structure your answers to get every single point.
Look, you've put in the hours, you know this physics, and now you have a clear strategy for the exam itself. Trust your prep. Be methodical. Execute the plan we just walked through. You are ready for this. Go in there and show what you know. Good luck.